Let us continue the previous session, EE5508, Optical Processes in Semiconductors. In the last session, we discussed high doping effects in semiconductors. Let us recap on these topics. At high doping concentration, there are several characteristics of the semiconductor changes. Changes in the impurity ionization energy, density of state near the band edges, changes in the absorption edge, changes in the band gap energy, and the respective effect of the Mott transition, band tailing, Bernstein mode shift, and band gap narrowing. As we have mentioned, there is a critical concentration where the Mott transition start to occur. And we define the Mott transition when the semiconductor is heavily doped with shallow impurity and the donor level or the acceptor level, the wave function broaden and overlap with each other, and they form the impurity band. And this impurity band increases with the carrier concentration and it overlaps with the conduction band. So this is a transition from a localized state, which is at the donor or the acceptor level, to the conduction band, and that is known as the Mott transition. So when the carrier concentration is low, that is a low doping. As we mentioned, the impurity state is isolated and discrete, and they do not interact with each other. And in medium concentration, the adjacent impurities start to interact, split, and finally form impurity band. At even higher concentration, the impurity band widen and merge with the conduction band. Now, for hopping conduction, especially at low temperature, where the carrier concentration is low, the carrier at the donor state cannot be thermally excited to the conduction band at low temperature. The thermal energy is low. So the only way the electron at the donor can transport is to hop from one impurity state to another. Okay, but they do not have enough thermal energy to promote to the conduction band. So this is known as hopping conduction. Although the thermal energy is low at low temperature, you expect to have this kind of hopping conduction, and with a little of thermal energy, the electron basically can tunnel from one state to another, or we know this as a hopping conduction. Now, impurity band at medium concentration, the carrier basically can propagate inside this band. So this impurity band has a bandwidth of delta E and is measured proportionally to the cube of the doping concentration. So as the impurity band widened, you'll start to merge with the conduction band. So that is known as the Mott transition. And in order to calculate the critical concentration when the Mott transition occur, this is the Mott criteria. We will not derive a rigorous equation for this Mott criteria. I will just take the equation. So AB is basically the effective ball radius of the donor. And the ball radius basically can be calculated, okay, from this formula. And the ME star is the effective mass of the donor. And since we use the hydrogenic model, where the donor in the semiconductor can be modeled after a hydrogen atom, so the donor effective mass, we will take it as the electron effective mass of the gallium arsenide. AH is the ball radius of the hydrogen atom. So for hydrogen atom, we said that the lowest orbit that the electron that is orbiting around the nucleus, that is the Bohr radius. Similarly, for donor, okay, the electron basically orbiting around the donors, and the lowest orbit have the smallest Bohr radius, and is known as the Bohr radius of the donor. Next is the band tiering. As we mentioned before, okay, there's a random distribution of the charge impurity that causes the potential fluctuation in the band edges. So in the anode semiconductor, the potential fluctuation is absent. The band edges are well defined. So in the E, as a function of spatial diagram, you draw two straight line. And for energy as a function of K, you expect to have a parabolic dependent. That means E is proportional to K squared. So like a second order polynomial kind of curve. Now, with in the high doping concentration, you expect there's a band tiering effect. So the state actually tear into the forbidden gap. So if you dope with semiconductor with shallow impurity, let's say donor, you excite from the top valence band, okay, just below the bottom of the conduction band. Because there's a band tiering effect, there will be band edges. So the absorption rate will start below the fundamental gap. And then we'll talk about Bernstein mode shift, where if you dope heavily in the dope heavily for the semiconductor, the effective mass actually sits inside the conduction band. So below the Fermi level, all the states are filled. So in order to excite the electron from the valence band to the conduction band, you have to overcome this level or this delta, which is the electronic energy level, because all these are filled. So the effective absorption age is no longer the fundamental gap, which is near the top of valence band to the conduction band, but you have to overcome this delta value. So the Bernstein mode shift can be calculated, as we have discussed, based on this equation. And the wave vector K is now the Fermi wave vector, as we discussed in Prof. Wu's course. The N is the doping concentration. Band gap narrowing, K, is another effect and is in competition with the Bernstein mode shift. At very high doping concentration, the band gap actually shrink. And the way it shrink is there's an increase in energy of the valence band maximum and the decrease in energy of the conduction band minimum. So sometimes this band gap narrowing is also called the band gap shrinkage or band gap renormalization. And this is as a result of they have many carriers due to the high doping effect. Then you have electron and electron interaction. You can have hole interaction, so on and so forth. And this result in the reduction in the band gap. So this is a schematic diagram, okay, basically to illustrate the Bernstein mode shift in competition with the band gap narrowing. So the left panel show without any doping concentration. So this is defined as the fundamental gap. We call that EG naught. Once you dope heavily with the semiconductor, heavily, the fundamental absorption rate changes. So if you measure near the top of valence band to the conduction band, okay, you have to take in count the Fermi level is inside the conduction band. So you can see that the absorption H, okay, will have a higher photon energy compared to the original fundamental gap. Now, then there's also another effect due to the band gap narrowing, where the valence band rises. You can see that compared to this, and then the minimum of conduction band lower. So the minimum of conduction lower. So this band gap, okay, is smaller than this band gap without doping concentration. But however, you still have Bernstein mode shift, so the absorption H still again on the near top valence band to up to the Fermi level and above. So this absorption H compared to this absorption H of the photon energy, okay, is smaller in terms of magnitude. So in this diagram, you have a combined effect of the Bernstein mode shift as well as the band gap narrowing. Now, I thought I will explain again on the absorption coefficient as a function of energy for a N-type gallium arsenide. Basically, the gallium arsenide is doped with N-type shallow impurity and measured at 297 K, which is at room temperature. So the red curve is the high purity gallium arsenide without doping, okay? And then the red, blue, green, and orange is in the increasing order of the carrier concentration, okay? So at high purity, you can see that the absorption coefficient decreases drastically. Or another way to look at it is the absorption coefficient increases rapidly as you increase the photon energy. So to be consistent, it will be easier to say that the high periodic gallium arsenide exhibit a rapid increase at the fundamental gap. So basically, you can see that as you increase the photon energy, the absorption coefficient increases rapidly. Next, you can see that as the concentration increases, okay, all the absorption curve actually shift to the higher photon energy. So shift to the higher photon energy. This is due to the Bernstein mode shift. And you can see for each absorption curve, okay, the blue, the green, and also the orange, there's this exponential decay of the absorption coefficient. This is due to the band tailing effect, which is the formation of the tail state. Okay, next, we have to look at the high purity gallium arsenide actually exhibit a rapidly rise in the absorption curve. How do we understand this curve? I thought that I'll give you a schematic diagram to illustrate the concept. This is the energy as a function of carrier concentration. And you have learned in Prof course, this is based on the Fermi-Dirac distribution. Okay, near the conduction band edge, okay, the carrier concentration basically have a lot of state. And then it decrease, okay, exponentially. And for the whole, again, near the valence band, it also decreases as you go further down the energy level. So imagine that you have a Fermi level down here for an intrinsic semiconductor. Okay, so below the Fermi level, all the electrons are filled in the valence band. Okay, And then if you come in with a photon energy, you can excite the electron from the near the top valence band to the conduction band. So there's a lot of available state for the electron to occupy. So electron can easily fill up, okay, near the conduction band edge. Okay, so this is the energy as a function of carrier concentration. So there's a lot of state for the electron to occupy. So the electron concentration, okay, can occupy near the conduction band edge. So there's a rapid rise, okay, in the absorption curve. So carrier making a transition from the valence band to the conduction band because all these states are nearly empty. So there's a possibility for all the electron to occupy near the conduction band edge. However, for a degenerate semiconductor, where the semiconductor is heavily doped, so then your Fermi level will start to move up. Okay, this is still below the conduction band edge, so doped with N-type. As you increase further, the Fermi level will go inside the conduction band. So below the Fermi level, all this state will be occupied by the electron, which means that there will be less available state, okay, above this Fermi level. Again, you can look at this diagram. If the electron is occupied, okay, near the band edge, as you go further down, there will be less state for the electron to occupy. So then you expect the absorption coefficient to decrease. So you can take any value, let's say at 1.43 eV. Okay, if you draw a vertical line, you can see that the absorption curve for high purity, the absorption coefficient drop from the high purity, which is no doping concentration, to high doping concentration. As the absorption coefficient actually drop in value, okay, for a particular photon energy as you increase the carrier concentration. So the absorption coefficient actually drops in value as you increase in the carrier concentration. Okay, so you can see that the absorption coefficient is reduced because many of the states in the conduction band are already occupied. So if you go further, you move your Fermi level further up, more and more is occupied, which means that less available state, the electron can be promoted from the valence band to the conduction band. So there are less available state for the electron to be occupied. So eventually, they will reach a level, there are no available state for the optical transition, okay, as you keep increasing the Fermi level. So the absorption coefficient actually decreases, okay, as the concentration increases. And this is indicative of the band gap narrowing effect. And you also expect the increase in the absorption coefficient, okay, this rise is abrupt, or the slope is very steep. Compared to those high doping concentration, the slope is very gentle. That is because there are less available state for the electron to be promoted from the valence band, okay, above the Fermi level. Because below the Fermi level, most of the state are already occupied. Now, for gallium arsenide doped with p-type, there's also Bernstein mode shift, and there's also band gap narrowing effect, and there's also the band tailing effect. Very similar to the N-type gallium arsenide, which is doped with N-type doping. The only difference is You can see the absorption curve as you increase the doping concentration. For example, the red curve is 1.6 times 10 to the power 16. Okay, the orange curve is 1.6 times 10 to the power 19. So the absorption curve actually shifted to a lower photon energy. For the N-type, you shift the higher photon energy. Okay. Now, in P-type, there's also Bernstein mode shift. However, the Bernstein mode shift is less prominent compared to the N-type semiconductor. The reason is because the Bernstein mode shift is inversely proportional to the effective mass. So the whole effective mass is heavier. So Bernstein mode shift inversely proportional effective mass. You expect the Bernstein mode shift to be smaller, okay, in shift in the photon energy compared to the N-type semiconductors when you dope it heavily, okay, with shallow impurity. And as a result, don't forget that you still have band gap narrowing. So if the Bernstein mode shift is less prominent, then the band gap narrowing effect, okay, can be clearly seen, and it drops in the absorption curve and it shifts to a lower photon energy. So you can see that if you refer to the previous diagram, okay, if the Bernstein mode shift, okay, is less prominent, then the band gap narrowing effect become predominant. So you expect the fundamental absorption edge actually to decrease even further. So as a result, there's a shift in towards the lower photon energy because the band gap narrowing effect is more predominant compared to the Bernstein mode shift. Okay, let's conclude our previous session on the high doping effect in semiconductors. In session 2.5, we will discuss the radiative transition in semiconductors. Now, because of the time constraint, we only study the radiative transition instead of the non-radiative transition. Okay, non-radiative transition will involve defects in semiconductors and also involve phonons. Okay, for this session, we'll discuss the radiative transition. We'll study the optical processes that involve the emission of radiation from the sample. And one of these processes, the emission, okay, is the luminescence, while the other type, okay, is due to the inelastic scattering of the light. For example, Raman scattering or Boring scattering. So basically, the electron interact with the lattice and get scattered, and there's also emission of light. But such a light is usually weak in intensity. So for us, we are studying only the luminescence process. In luminescence process, electron basically can be excited from near the top of valence band to the bottom of the conduction band. Okay, either electrically or by optical means. And some of the energy will be lost as an excited electron return to the ground state by emission of light. So in order for a sample to emit radiation, it has to be energized by some external means. So briefly, we'll talk about electroluminescence, photoluminescence, thermoluminescence, and cathode luminescence. It's easy to understand the electroluminescence process. Basically, you can have a PN junction, so you apply current or voltage to the PN junction, and then you can have a light emitting diode, and the active layer will give out the emission of light. So that is electroluminescence. For photoluminescence, you come in with a photon energy, for example, a laser with a certain photon energy greater than the band gap. So you excite the electron from the bottom, from the top of valence band to the conduction band. Okay, this photon energy must be at least greater than the band gap. And then at the conduction band, it later recombine with the hole to give out light near the band gap energy. Now in thermoluminescence, basically you are using heat or temperature, okay, to cause the emission of light. So thermoluminescence can be used to study defects in semiconductor, and such defect actually introduce electron trap or hole trap, okay, in the band diagram or in the energy level inside the band gap. So in typical thermoluminescence measurement, you basically coming with a photon energy, okay, that you can excite the electron from the valence band to the conduction band. So you come in with photon energy, you excite the electron from the top valence band to the conduction band, and then you get trapped in the electron trap. So these electron trap are due to defect, which introduce a defect level in the band gap, and we call this the electron trap. Although not all are being trapped at the electron trap, some may recombine with the hole. Now, after you remove the photo excitation, that is remove the incoming light, okay, you do a heating by basically injecting the electron from the electron trap to the conduction band. So this is known as the thermal stimulation. So after you remove your excitation of the light, the heating inject enough thermal energy into the system, so you provide the trap carrier, which is down here, the electron, with energy sufficient enough to escape from the trap to the conduction band. Okay, so you basically release the electron into a conduction band, and it can either recombine with the hole in the valence band, or some of it can be trapped at another level, which we call the recombination center. And this is sometimes called the color center, where you can have light emission after the electron recombine with the hole down here. So this is known as the thermoluminescence. Now for cathode luminescence, okay, basically you're using a very high energy electron beam. For example, you can use a scanning electron microscope, and you can, okay, come in with a very strong high energy electron beam to impinge onto the semiconductor. This electron beam basically have an energy of 1 to 40 keV. And the way we look at it is that this high electron beam or energetic electron, when it hit onto the semiconductor, it can knock the electron out of the covalent bond in the semiconductor by impact. So this is known as OJ impact generation of carrier. So those electrons that get knocked out of the covalent bond are the secondary electron. Okay, in turn, they can scatter other electron. So you can expect to have a cascade of scattering event to generate many electrons. For example, 10 to the power of 3 secondary electron per incoming incident electron. And this secondary electron can excite again from the valence band to the conduction band. And then this electron can recombine with a hole in the valence band and create photon energy. Now, compared with photoluminescence, you are basically coming in with a photon energy. Here, you are basically coming in with an electron beam, okay, of energy 1 to 40 kilo electron volt. This probably is in a few tens of EV. Okay, so for example, you can use energy in like 1.24 to 2 EV. Okay, but here you're coming in with a high electron beam with high kinetic energy. Now, one advantage of exciting with electron beam is that the band gap of the material are investigated is not limited by the energy of the incident light. So you have to come in with a specific photon energy or particular wavelength of photon energy that is greater than the band gap energy. So this wavelength is, or the photon energy is specific. Down here, you are not limited by the energy of the incident light, as in the case of the photoluminescence. So in the scattering electron microscopy, okay, when the focus beam, okay, that impinges on the sample, it will emit light, okay, and collected in the optical system due to the impact ionization process, impact OJ generation process. And you can use fiber optics basically to collect the light and transfer the light out of the microscope, and then can be detected by a detector. Since this is a microscope electron beam, you can scan the electron beam in the XY direction, in the XY pattern. So you can measure the light emitted with the beam at each point. So you have the sample, okay, become an electron beam. As you scan the sample, okay, in the XY pattern, you're measuring, okay, a lot of points in the sample. So you are measuring an area. So you are basically doing a mapping. So this is not a cathodoluminescence imaging. And the optical properties, of course, which is the light emitted from each, okay, point, can be correlated with the structural property observed with the electron microscope. So by measuring the photon energy dependence for a fixed point or a certain area, the spectral characteristic can be recorded. Now, let us discuss more detail for photoluminescence mechanism. For photoluminescence, basically the incoming photon energy, okay, as long as the light intensity, okay, is not too high, this is a non-destructive process. Or this is a destructive process because it's coming with a strong electron beam, okay, and then you are impinging with high electron energy, and you knock out electron from covalent bond. Here, photoluminescence basically exciting the electron near the top valence band to the conduction band, and then recombine again with the hole and give out photon energy. The photoluminescence mechanism involves three separate steps. First is the excitation. You come in with a photon energy must at least greater than the band gap energy. Okay, and then you excite the electron near the top of the valence band to the conduction band. Next, electron cannot stay at the high excited state. It has to be relaxed down to the bottom conduction band. So this is known as thermalization. Similarly for hole, okay, you bubble up to the top of the valence band. So this relaxation is known as thermalization. So the excited electron hole pair will relax down to the quasi-thermal equilibrium. by emitting phonon energy, which is the heat energy. So this relaxation of the electron, okay, by emitting phonon, the heat energy, is in the picosecond range. Okay, after the electron relax to the bottom conduction band and hole relax to the top valence band, the electron and hole can recombine. So this is recombination process. So the thermalized electron and hole recombine radiatively to produce emission of photon energy, okay, equals to the band gap energy. And the recombination process usually is in the range of nanosecond. Now, let us establish some of the equation for the radiative recombination rate. Let R be the radiative recombination rate at non-equilibrium, which means that when you come in with a photon energy to excite the electron from the valence band to the conduction band, you are perturbing the sample because you're coming with an external source of energy. And therefore, the semiconductor is at non-equilibrium condition. So this radiative recombination rate, basically how fast does the electron and hole recombine. So this is a recombination rate. It has to be depends on the product of the number of electron produced, okay, and also the number of hole at the valence band. So R will be proportional to the electron concentration at the conduction band and the hole in the valence band, because electron and hole eventually will have to recombine. If we put an equal sign, this R is the proportionality constant, and we call that the probability for radiative recombination, or sometimes we call that the recombination coefficient. We will approximate the R, the recombination coefficient, and non-equilibrium condition to be approximately the same as the one at the equilibrium condition, which is R naught. So R is approximate to R naught. The recombination coefficient at non-equilibrium is equals to the, or approximately equals to the equilibrium condition. Now at thermal equilibrium, okay, if you don't come in with any external source to protect the sample, then the recombination rate R naught will be R naught, it will be equals to small r naught n naught times p naught. Okay, and n naught and p naught, okay, based on mass action law, equals to ni squared. I re-express my radiative recombination rate at non-equilibrium to be in terms of the recombination rate at thermal equilibrium. So you can basically substitute R naught, okay, with big R naught divided by ni squared. That will be the recombination rate in terms of the at non-equilibrium in terms of recombination rate at equilibrium. So when the radiative recombination rate at non-equilibrium is equals to equilibrium condition, then MP will approach the equilibrium intrinsic value, which means that when MP, okay, is equals to Ni squared, then Ni squared R will be equals to R naught. In optical transition or optical process in semiconductors, essentially there are 5, okay, without taking into account some other recombination at the non-recombination center or the non-radiative recombination center. So first is the band-to-band transition, conduction band, and valence band. The other one is the free electron in the conduction band to the acceptor level. So this is called free to bound transition. Or you can have donor, electron and donor, transit to free hole in the valence band. And you can also have donor making the transition to the acceptor. Last but not least, you can have also optical trap, or basically due to defect level. So electron trap at the defect level, or making a transition to the valence band. This is known as the band trap optical transition. First, let us look at the band-to-band transition, which involves the recombination of free electron in the conduction band and hole in the valence band. At a given temperature, let us recap that the intrinsic carrier concentration of a semiconductor, can be expressed in this equation, where it depends on the band gap and also depends on the temperature. So the larger the band gap for a semiconductor, the intrinsic carrier concentration will be small. Now at thermal equilibrium, based on the previous discussion, the recombination rate will be R naught, N naught, P naught. N naught, P naught is Ni squared. And this is equals to Gi, where Gi is the thermal generation rate of the electron hole pair. So at thermal equilibrium, there's no external source. And if you just put a sample in the shell, you expect there is some kind of thermal generation of the electron and hole. And this electron and hole will recombine. So the recombination rate will be equals to the thermal generation rate, of equal number of electron and hole. Now, let us shine some lights, with the incoming photon energy to excite the sample or to perturb the sample. So now the condition will become non-equilibrium. So the optical generation rate, we call it GOP. OP stands for optical, will be added to the thermal generation rate. So now your carrier concentration, will increase to a new steady state. And remember, we approximate the recombination coefficient in non-equilibrium to be the same as the equilibrium condition. So at non-equilibrium state, the recombination rate will be Gi, the initial thermal generation rate, plus the external source, to excite additional electron hole pair. This is the generation, due to optical means equals to R and P, so no longer N naught, P naught, this is non-equilibrium condition. So we approximate R to be R naught, NP can be re-expressed as N naught plus delta N, which is the excess carrier generated due to the optical means or the incoming photon energy, and P naught plus delta P. Delta P is the excess hole that generated, due to the incoming photon energy. If there's no traps, for steady state recombination, we assume equal number of excess electron and equal number of excess hole generated. So delta N equals to delta P. You multiply, and expand this term to be of this form. Replace delta P with delta N. So you will get this equation. And don't forget that on the right-hand side, you have R naught, N naught, P naught. And this term is basically GI. Okay? GI is R naught, N naught, P naught. So it cancels off with the left-hand term, GI. Okay? And if the incoming photon energy is not of too high intensity, we call this the low-level excitation, then we neglect delta N squared. So after you cancel off the term of GI, you left GOP equals to the rest of the term. And you drop delta N squared. So you have this term. And then I re-express the R naught, N naught, P naught as the denominator by saying 1 over the term, which is the same as this term. And I call the denominator, okay, for this term as tau. So tau is equals to 1 over R naught, N naught, P naught, which has a unit of time, okay, second. Okay, this is known as the minority carrier radiative lifetime. So the recombination coefficient R naught is measured cm cube per second. R naught is per cm cube. So dimension 1 over second, you get a second in unit of time. So we define the minority carrier lifetime is basically the average time in excess the minority carrier will survive in the sea of majority carrier. Imagine you have a PN junction and then you apply a 4 bias. Electron in the N region, okay, will basically transport to the P region. So in the P region, the electron is actually the minority carrier and it will recombine with the whole. So basically, the minority carrier lifetime measured, okay, how long it will stay in the P region before it recombine with the whole. Minority carrier lifetime is an important material parameter. Depends on the concentration of bit level and purity. Okay, if you have a defect, you introduce dip level in the band gap and you will trap the carrier, then you affect your minority carrier lifetime. And of course, it also depends on the crystalline quality of the material. And the minority carrier lifetime will depend on the material per se. It can be vary a few nanoseconds to a few milliseconds in silicon, depending on the quality. So let us see, okay, further for intrinsic semiconductor, okay, the minority carrier lifetime is we express down here 1 over R naught, N naught, P naught. In intrinsic case, N naught equals to P naught equals to Ni. So this term will be 2 N naught. So it depends on the intrinsic carrier concentration for the minority carrier lifetime. If the material is P-type, then we expect P naught will be much greater than N naught. Then you drop N naught term, so the minority carrier lifetime will be 1 over R naught P naught. So for all these cases, it's for low-level injection, low-level excitation, which means that the incoming photon energy, the intensity is not that intense to excite many excess carrier of electron in hole. For high-level excitation, okay, the incoming photon energy is so intense that it can excite many electron hole, then you cannot ignore the delta n squared. So we go back to this expression. Okay, this R naught, N naught, P naught cancel GI. So the G optical generation, okay, will be of this form. And then you factor out the delta N. And then you re-express, okay, in terms of the recombination lifetime. So 1 over R naught delta N, where delta N, okay, is much greater than the N naught and P naught, the equilibrium carrier concentration. So the tau is 1 over R naught times delta N. So N naught and P naught we can ignore. This table basically shows the minority carrier lifetime in several semiconductors at room temperature. So this is the material, silicon germanium indirect semiconductors, gallium arsenide, gallium antimonide, indium arsenide, indium antimonide are direct bandgap semiconductors. So 1.12 EV for silicon indirect bandgap, 0.66 EV for germanium indirect bandgap. So all these values are the direct bandgap energy for this material. Intrinsic carrier concentration, okay, don't forget that it's proportional to the power of minus Eg over 2 kT. So you can see that as the band gap, okay, increases, the intrinsic carrier concentration actually smaller. So for example, gallium arsenide is 1.423 EV, okay, is greater than the gallium antimonide. Okay, the intrinsic carrier concentration is 10 to the 6 compared to gallium antimonide is 10 to the 4th to 10 to the 14. Now, if we look at silicon, okay, this is the recombination coefficient and it can be measured experimentally. So we'll just quote the value here. The recombination lifetime, okay, for intrinsic semiconductor is 2R naught N naught. So if you plug in these two values, you realize that minority carrier lifetime is 6.8 hours in silicon. If you do it with p-type, okay, so the recombination lifetime will be of this expression. So let's say p naught is 10 to 17, you reduce to 5 milliseconds. So you can see that the silicon, okay, in view of the fact that it's an indirect bandgap semiconductor, the recombination lifetime in intrinsic semiconductor is 6.8 hours. It's not very efficient for light emission. You want to have the recombination lifetime to be as short as possible, so that when the electron is injected, let's say from N-type to P-type, you want it to be quickly recombined with the hole. Even though you do it with P-type or shallow impurity of the acceptor, you can only reduce to 5 milliseconds. Usually for light emitting diode, you expect this kind of recombination to be in the range of nanosecond. So remember, tau is 1 over R naught plus P naught. Okay, for low level excitation, for high level excitation will be R naught delta N. Now compared to gallium arsenide, if you measure for intrinsic semiconductor, the recombination lifetime is 6.3 minutes. However, if you dope with p-type, okay, 10 to 17, you can change the recombination lifetime to 13.9 nanosecond. So that will be good for gallium arsenide can be used, okay, for emitting devices. Radiative efficiency. Basically, how efficient is for the semiconductor to emit light. So if you have a conduction band and you have a valence band, and then if you promote the electron to the top valence band today, and leave a hole behind the conduction band and electron and hole recombine to give up photon energy. So the radiative recombination rate by emitting this photon energy will have a recombination lifetime. That is how fast the electron and hole can recombine. The faster, the better. If you introduced, or because the semiconductor is imperfect, you introduce a defect or energy state, or we call it an intermediate state or non-radiative state, then the electron can get trapped in this intermediate state. And this process is non-radiative. Okay, it does not give out light in most cases. So you also have a non-radiative recombination lifetime. So the effective recombination lifetime will depend on the radiative lifetime and the non-radiative lifetime. So it is expressed in this form. And the radiative efficiency, okay, again, is expressed in this form as the efficiency will tend to 0 if the non-radiative lifetime is 0 or tends to 0, which means that most of the electron will recombine at the intermediate state, okay, because this recombination, the lifetime is shorter. It takes a longer lifetime for the electron to recombine with the hole if this lifetime is much shorter. Now, if the non-radiative lifetime tends to infinity, which means that this recombination lifetime is very long, then the probability of electron and hole recombine will be much faster. Let us look at one example. A very short laser pulse at this wavelength of photon energy, 780 nanometer, okay, is incident on the thick gallium arsenide sample with an absorption coefficient of 1.5 times 10 to the power 6 per meter at this wavelength. The pulse has energy of 10 nanojoules and is focused on a circular spot of radius 100 microns. So the laser have a circular spot radius of 100 micron, okay, focused onto the sample surface. Calculate the initial carrier density at the front of the surface. If the radiative and non-radiative lifetime of the sample is 1 nanosecond and 8 nanosecond respectively, calculate the time taken for the carrier density to drop to 50% of the initial value. And calculate the total number of the photon generated, okay, by each laser pulse. So let n be the incoming photon number, okay, and delta n be the number of photons absorbed within the slice of the sample, which is delta x or tx. So this incoming photon number and this outgoing photon number. So the outgoing photon number will n minus delta n. So sum of the delta n, okay, will be within this slide. So the delta n, the number of photons absorbed in these slides, okay, will be n times this delta x, this thickness, of course, multiplied by the absorption coefficient, because that determines how much the photon has been absorbed. Now we assume that the absorbed photon, each absorbed photon generate electron hole pair, which means that the number of electron and hole generated is equal to the number of photon absorbed. So one photon generate one electron and hole pair. So the carrier density generated will be delta N divided by the volume. Remember, the carrier is dependent on, is measured in per cm cube. So delta N is the outgoing photon, okay, number of, the delta N is basically the number of photon absorbed, which generate the electron hole pair. So one photon generate one electron hole pair. So the carrier concentration, okay, generated will depends on the number of photon absorbed and per unit volume, which is area times the thickness dx. So delta N, you just express alpha N dx, substitute into this equation, and then dx and dx cancel, you have alpha N over A. Now, remember that the number of photon, which is N, the incoming photon number in the laser pulse, will be equals to E over H bar omega. E is basically the pulse energy, which is 10 nanojoules. And your incoming photon is at the wavelength of 780, which you will convert to 2.83 times 10 to the power minus 19 joules. Okay, you convert to energy will be 2.53 times 10 to the power minus 19 joules. Okay, one photon is at the photon energy of 2.53 times 10 to the power 19 joules. And you have the pulse energy, okay, of 10 nanojoules. So 10 nanojoules divided by the photon, incident photon energy, that gives you the number of photon. Which means that I can calculate N. Since I know alpha, I know the area of the laser spot. Okay, the area of the laser spot can be calculated as pi r squared, since the radius is given to you, 100 micron. N can be found by 10 nanojoules divided by 2.53 times 10 to the power minus 19. Alpha absorption coefficient is given to you. So you just plug in all the value, area, pi r squared, all convert to SI unit. Alpha 1.6 times 10 to the power 6 per meter. Energy 10 times 10 to the power minus 9 joules, since it's 10 nanojoules. And this is the photon energy. Remember, given the wavelength, you can convert to EV and you can convert to joules. So the carrier density, okay, has been generated is 1.9 times 10 to the power of 24 per meter cube at the front of the surface. Calculate the time taken for the carrier density to drop to 50% of the initial value. Now, in this sample, you also have non-radiative lifetime, which means there are also defect state. So the effective recombination lifetime will depend on radiative and non-radiative lifetime. So you just need to plug in these two values, you get about 0.9 nanosecond for the effective recombination lifetime. So this carrier concentration is basically at time equal to 0 generated at the front surface. So now we want to know this carrier after it recombine, how much does it decrease by 50%. You can express the carrier concentration, okay, in terms of the exponential decay, just like in the intensity, okay. The absorption coefficient, okay, the intensity is dependent on the exponential decay, where I equals to I naught E the power of minus alpha x. So in this case, it's n naught exponential minus t over tau, where tau is the recombination lifetime or the time constant. So you can see that as time is 0, the initial density is n equals to n naught, which is this value. Okay. As time goes to infinity, the carrier concentration is 0. So you bring n naught over, nt over n naught is equal to half, since it's 50%. T is the time that you want to find by decreasing the carrier concentration to 50%. And then tau is this value, 0.9 nanosecond. So T, it will be 6.2 nanosecond for the carrier to decrease by 50%. Now, what is the efficiency? The total number of the luminescence photon generated by each laser pulse. Remember, there's non-radiative lifetime, which means there is a defect state or energy state, okay, which are non-radiative to capture your carrier. So the efficiency may not be 100% for the semiconductors for radiation. So the efficiency will be 1 over tau r over tau nr plus 1, based on the previous equation. You plug in tau r, tau nr. So the radiative transition or efficiency is 89%. So based on this diagram, okay, you have this intermediate state or non-radiative state or trap state. So your efficiency is not 100%. So you have to use this equation by plugging in the value of tau r and tau nr. And you get 89%. Now, each laser pulse contains e to the power of h bar omega. Remember the energy, okay, from the pulse is 10 nanojoules. And this is the incoming incident photon energy. So this gives you the number of photons for each laser pulse. So if we assume all the laser photons are absorbed in the crystal, so the number of photons re-emitted will be this value times 89%, which is 89 efficient for the radiative emission. Okay, 89% of the photon will be emitted. So E over h bar omega times 0.89, and this is the number of photon, and that you can plug in the value 10 nanojoules. This is the incident photon energy times 89%. That gives you 3.5 times 10 to the power of 10 photon. We shall stop here before we go to the next session to discuss the photoluminescence experiment.